Okay, I think we can start. Let me run the application. All right. So hello, everyone. Hope you're doing well. Welcome to this workshop series on artificial intelligence. Today is going to be the second course, the deep learning course. But before we dive into the course, allow me to introduce myself again, just in case there are new participants. So my name is Abdelghafour HALIMI. I have a PhD in image processing and artificial intelligence from the National Podcast Institute of Toulouse in France. And I was working as data scientist for worldwide leading companies, such as Pierre Fabre and Atos in France. And I have over a decade of experience in the AI field, working for several projects for different fields, like remote sensing, medical imaging, computer vision, with major organizations such as Airbus, CNES, or the European Space Agency. And I recently joined the Causalization Core Lab. So our Core Lab provides a lot of facilities and expertise in various fields. For example, my colleague James is specialized in 3D data visualization, Ronald in AR, VR, and me and Didi in the data science fields. So don't hesitate to contact us. I put you here link for our wiki page, where you can find all the details and information about the different services that we are providing and how to book all these facilities. You can check also our YouTube channel, where you can find the previous tutorials and training provided by me and my colleagues. All right, let's start by a brief summary and some key points of what we have already covered last course. We have seen the meaning of machine learning. Machine learning is using algorithm or a computer program in order to learn some patterns in the data, and then using that algorithm, what it's learned, in order to make some prediction on the future on new similar data. We have seen also the difference between traditional algorithm and machine learning algorithm. Traditional one gonna start with an input and a set of instructions in order to get the output. Machine learning, on the other hand, gonna start with an input and an ideal output. You're gonna try to figure out the right instructions. We have seen also when we shouldn't use machine learning. If you can build a simple rule-based system, go for it. Forget about machine learning. It's a waste of time. This is the best model you can get. Actually, it's rule number 1 of Google's machine learning handbook. Okay? Now, what is deep learning? I mean, deep learning right now is a buzzword, right? But in reality, it's just a type of machine learning algorithm who's going to use neural networks to learn these patterns. Let's see a small example of it. Where classic machine learning algorithm is going to use statistical methods to learn these patterns. For example, if you want to predict if from this image if it's a male or female, machine learning algorithm is going to start by extracting some features. Maybe the roundness of the face, the distance between the eyes, the distribution of the pixel intensity, and then, based on these features, you're going to build the classifier. Supervector machine, random forest, XGBoost. You can choose wherever you want in order to predict if it's a male or female. Now, deep learning is going to do exactly the same thing, extracting these features and doing the classification, but in an automatic way using neural network. Again, I'm not going to enter into the mathematical details behind this. But you can see it as black box. We're going to do the job of learning these patterns and doing the classification. Now, another illustration of it, you can see that artificial intelligence is going to be an advanced technology that's going to mimic the human intelligence and behavior. Machine learning is going to be a subset of AI. We're going to use statistical methods to learn this pattern from analyzing the data. And finally, deep learning is going to be a subset of machine learning that's going to use neural networks to learn these patterns. Now, why should we use deep learning? I mean, a good reason could be, why not, right? Of course, but of course, a better reason. For a complex problem, can you think of all the rules? Probably not. I mean, if I'm going to ask you right now to build the self-driving cars, can you think of all the rules? Impossible. It's going to take you years. Deep learning can do it easily. Now, there are many other reasons why deep learning is good for. For example, for problems with a long list of rules. When the traditional approach is going to fail, deep learning can help. When the environment is constantly changing, deep learning is very good at adaptation and learning new scenarios. And of course, when you're working with a large collection of data, deep learning can easily discover insight from it. I mean, again, can you imagine trying to handcraft rules for what 100 different kinds of food looks like? It's going to take a while. Deep learning can do it easily. Now, there are other reasons where deep learning is not good for when you're going to need explainability. There's a problem with deep learning. The patterns learned by deep learning models are not interpretable by a human. I mean, if you take the previous examples, machine learning algorithm, the patterns learned by him, it's something a human can understand. Roundness of the face, distance between the eyes, the distribution of the pixel intensity. Deep learning, you cannot. It's not. It's going to be very hard for a human to understand what's going on behind these patterns and how he's learning this. When the traditional approach is a better option, again, if you can accomplish what you need with simple rule-based system, go for it. Same thing as in machine learning. When errors are unacceptable, again, deep learning models are probabilistic models. So they're going to give you a probability. If you're working with subject that must not have any errors, forget about deep learning, because at least they're going to give you a small error. It's a probability at the end of the day. And finally, when you don't have that much data, deep learning loves big data in order to produce great results. Now, here, again, not a rule. It's in general by experience. When you are working with structured data, CSV file, Excel files, tabular data, machine learning algorithm tends to be working the best. We have seen this with XGBoost, like GBM. When you are working with unstructured data, like images, audio files, text, deep learning tends to be working the best. Again, not a rule, it's by experience. You can start from it. Here, I selected some of the deep learning use cases, common one. We're going to find the recommendation systems, like the one used in YouTube or Netflix. We're going to find translation, speech recognition, computer vision to detect objects, for example, natural language processing, like the large language models, ChatGPT and others. And it's also adapted to do some classification and regression. Now, let's try to run live demos to illustrate the computer vision algorithm. Again, you know how it goes with the live demo. I don't promise anything. Let's try and see how it goes. Let me run this. Okay. Let's start the first one. All right. Let me choose, OK. Perfect. Here, this is an example of 3D hand gesture, which means, as you can see here, at the end, no hand. But as long as I put my hand, it captures my fingers and recognize my hand very well. And it can manipulate virtual object, as you can see. Add some particles to it, manipulate it, zoom in it, change the object, as you can see. And this is running locally on my machine. Why this is important? You can see it as resolving a remote assistance. This is an example of how you can do it, for example, to control a robot remotely, for example. We can go a little bit further. You can see how it's doing it very well. It's working very well. But you can go a little bit further and make it more precise, like this one, where I can write, as you can see. You see how precise is it? Why it's important again? Maybe for medicine, like I can see this, hello. You see? It's working very well. I can change the color. I can remove, clean everything. For medicines, to do surgery remotely. And it's a big thing right now, because now with the 6G, This is the problem that they are working on, like reducing the latency, increasing the bandwidth. This is the kind of stuff that you can do with computer vision. And you can see how it's very precise. Running again locally on my machine. Hope that it's not gonna crash for the moment. But again, this is an example of remote assistance using computer vision. It can be also a prior for augmented reality, by the way, also. You can see how you can manipulate your object. All right? Let's stop this. And try again to start the next one. Second one is object detection. It's going to take a little bit longer because it's a big algorithm. Let's see. Amazing. You see? It's working very well. So this is an example of object detection who is resolving two inverse problems here. It's not doing only the classification, but you can see also he's doing also the segmentation, which is amazing. You can see he's working very well. I don't know, like if I'm gonna put, cell phone, you see? Amazing. Now, let's try to take this a step further. Let's see. I'm gonna do a small thing. Amazing. Now it's working wirelessly on my computer. You can say hello to the camera. It's working very well, as you can see. Perfect. Now, why this is important? Because now this kind of stuff can be embedded into drones to do maybe monitoring or surveillance. It can be also to do not only surveillance and monitoring, but embedded also in the camera to detect the license of the car plates. And you can see it's working very good. The chairs, the persons. Now I'm gonna give you a small example of a use case based on this object detection. On how, let me stop this. Okay, of an example of people counting. Let's see if it's gonna work. This is a small use case that I produced. Okay, so it's trying to count people, I don't know, like now it's 6, 5, you see, it's working wirelessly, but this is a small example of how you can do it, like to manage the crowd or in the event to calculate using embedded camera the number of persons that attend. This is a small use case of what you can do with deep learning. This is cool, right? Amazing. But again, quick aside. Now, sometimes, let me stop this. Deep learning can be very, very dangerous. And you should be careful when using it. Why I'm telling you this? Because sometimes you can diffuse fake news, right? How? Deepfake. This is an example of a deepfake of me. As you can see, amazing, huh? It's working very well. This was done in my local office, using my local machine. So you can see how it's scary. Just by giving him the algorithm, an image of Elon Musk, Ryan Reynolds, Einstein, he was able to produce this kind of stuff. And you can see how it's performed. Very good, right? I didn't push the algorithm very hard. It was just a simple one. And you can see, by small knowledge of AI, you can produce this kind of stuff. Now, this example, you can see that sometimes it can get even more scary. Why? This was done with a recorded video of me. Now, nowadays, I can make it work live stream. So you are watching someone who's talking with We like, for example, with Elon Musk, but he's not Elon Musk. This is why it's getting very, very scary right now. So again, this is just a small, quick aside of the dark side of deep learning. Perfect. All right. At least my PC didn't crash for the moment. Perfect. Let's move on. All right. Now, here, I selected some of the most common machine learning algorithms. We have already seen this last course. Random forest, naive Bayes, XGBoost, for example, and some of the most common deep learning models, algorithms. We're going to find neural networks, fully connected neural networks, convolutional neural networks, recurrent neural networks, and finally transformers, and many, many more. Now, depending on the problem that you are working on, many algorithms can be used for both structured data and unstructured. Today, we will be focusing on these three: neural networks, fully connected neural networks, on other word, deep neural network, and finally, convolutional neural networks. I'm going to use TensorFlow for that. So what are these neural networks? This is a small example of an anatomy of a small neural network. You're going to find what we call the input layer. Here is where the data goes in here. So it's composed, as you can see, of what we call neurons or neural units. Here it's composed only of two. Then you're going to find what we call the hidden layer. This is where the model is going to learn these patterns. And depending on the problem that you're working on, you can use a small one like this one hidden layer with 3 neurons, or 100 of hidden layers with 100 of neurons. Depends on the problem that you're working on. And finally, you're going to find what we call the output layer. This is where it's called learned representation or prediction probability. And this is an example of it when you are working with unstructured data. For example, images, text, audio files. You're going to start by doing first numerical encoding. Deep learning loves numbers. You cannot understand images, so you need to do the numerical encoding first. Then you're going to choose the appropriate neural network, depending on the problem that you are working on and the complexity of the problem and the size of the data set that you're working on. This is where the model is going to learn the patterns, and then you're going to have the representation output, which is matrix of prediction probabilities. And finally, you're going to convert it into something a human can understand. For example, if you are working with images, is this ramen or spaghetti? If you're working with Twitter, like, is this tweet talking about machine learning or not? If you're working with audio files, you want to do speech recognition and transcribe this into text. Again, just to give you an idea what's going on this neural net. This is a mini neural net. The idea behind a deep learning, this is what goes in. So you have your data, which is X here. Then you're going to have your neurons. For each neuron, it's going to be exactly the same thing. It's going to be the same for all of them. You're going to have the Z of X and A of Z. Z of X is going to represent your model, Wx plus B. We call W and B the parameter of the model or the weight of the model. And then you're going to have what we call the activation functions. Can be sigmoid, rectified linear unit, a linear one, and it's going to give you the y hat, the prediction. Now, going from X to y hat, it's called forward propagation. Now that you get your y hat, the thing that you need to do is to fix a loss function or cost functions, which is here just an error between your prediction and the true value. Can be mean squared error, mean absolute error. And the idea behind deep learning training and learning is to minimize this error by using optimization methods like stochastic gradient descent, Adam algorithm, line algorithm, it depends. And you're going to update this weight W and B again and again until it converges and find the smallest error between the prediction and the true value. So going from y hat to X, it's called backward propagation. Again, this is just to give you an idea. Forget about it. Let's move on. So again, these are the main type of deep learning problems. We have already seen this: supervised learning, reinforcement learning, and transfer learning. Today, we'll be focusing on only supervised learning and transfer learning. These are the most common inverse problems related to supervised learning. We're going to find regression, classification, and computer vision. We're going to try to write codes for these three examples, but this time using neural network. Let's start with the first one. So neural network with regression. Again, regression is when you want to predict a number. So how much will this house cost, or how many people will buy this application? But sometimes, if you are working with computer vision, like we have seen before, you see this bounding box. You get in this by resolving the regression problems. How? You see this kernel, this coordinate, 13 and 90 were predicted by resolving regression problems. All right? Now, if we take an example of predicting the house, first thing you need to do is to build your deep learning model, right? You're going to need some input and output. For this example, the input is going to be the number of bedrooms, bathrooms, garage. So the first thing you need to do is to convert it. Remember these steps. Convert it in doing numerical encoding. We have seen this. We call this one-hot encoder, for example. Then the output is going to be the prediction, the price. And this comes from looking at a lot of examples from it. So you're going to train here on a lot of examples in order to be able to predict this value. And the shape is important. In our case here, the shape is equal to 3 because we are using 3 features. Bathroom, and garage represented as tensor. And the shape here is equal to 1 because we are predicting the price, one value. Now these are the regression evaluation metrics. The common one, we have already seen this, mean absolute error, mean squared error, Huber, or R2 score. And this, now the classification. Now classification means predicting if something, one thing or another. If you are working only with 2 options, we call this binary classification. Is this email spam or not? If you are working with more than 2 options, we call this multi-class classification. Is this patient healthy, having heart disease, or tumor? Sometimes you're going to find what you call multi-label classification. For example, what tags should be used for this article? Machine learning is talking about machine learning, representation, learning, artificial intelligence. If you take the example of medical patient records, same thing, you want to build your deep learning model, so you're going to need some input. The input here is going to be represented by these parameters: ID, weight, sex, heart rate, chest pain. And again, you're going to need to do numerical encoding for that. The output is going to be a matrix of the prediction probabilities here. And it's going to come from looking at a lot of examples. You need to remember this. Deep learning loves big data. So you're going to train on a lot of examples here in order to predict this matrix with the probabilities for each patient. The shape, same thing. It's equal to 5 because we are using these parameters: ID, weight, sex, blood pressure, and chest pain. And for the prediction, it's equal to 3 because we are resolving multi-class classification problem with 3 cases. And these are the classification evaluation metrics. We're going to find accuracy, precision, recall, F1 score, and confusion matrix. We're going to see this in Jupyter Notebooks later. And finally, convolutional neural networks with computer vision. Now, computer vision means only that you are working with images. That's all what it means, computer vision. So we're going to find what we call the binary classification. Is this image representing steak or pizza? Multi-class classification. Is this photo of sushi, steak, or pizza? And finally, what you have already seen, object detection, as the previous examples and live demo. Now, object detection here, we are resolving 2 inverse problems. The first one is a regression problem that resolves this bounding box, allows us to get the coordinate. And the second one is a classification problem, because we are trying to predict this object belongs to which class, cats or dogs. This is what it means when you are working with object detection. Okay, so if you want to build, for example, an app food that detects the different kinds of food, same thing, you're going to need your deep learning model, some inputs. Here, you are working with images, so the input is going to be the size of the image, the width and the height, and the color channel, RGB. Numerical encoding, always. Here we're going to normalize the pixel intensity, for example. And finally, you're going to have the matrix of the prediction that comes at looking at a lot of images. We're going to try to build this at the end of the course, this app. But the difference here is that we are not going to use artificial neural networks as before. We're going to focus on using convolutional neural network. Why? Because it's optimized and the best choice to work with images. It's going to give you great results when you are working with images. And you're going to see an example of it. Again, the size, same. You're going to have width, the height, the color channel, but you're going to add what we call the batch size. Why? Because you remember the example with 70,000 images? It cannot be fitted in my GPU memory, right? So you're going to add the batch size, which is just a subset that's going to allows us to go through the whole data. That's all. Then you're going to have the shape of the prediction, which is 3 here, for example, because we are predicting 3Ks. All right, we're going to try to build all these 3 examples using the library TensorFlow. What is TensorFlow? It's an end-to-end platform for deep learning built on Python. It's able to access to many pre-built deep learning models, allows us to go through the whole stack, pre-processing the data, modeling it, and deploying it. And of course, it was originally designed by Google. Now, why TensorFlow? Again, because it's easy to model with it and to deploy it. But the most important part, it's compatible with GPUs and TPUs. And this is very important when you are working with deep learning algorithm. You want your model to be compatible in a library that you're going to use, compatible with GPUs, because it's going to take you millions of calculations. And to accelerate this, you're going to need the power of the GPUs. All right? So what you're going to try to cover today, again, we're going to try to go through these different steps. First one, getting the data ready, which means we're going to try to turn all the data into numbers first, make sure all the tensors are in the right shape, and finally, we're going to do what we call scaling the features, normalizing them, because neural networks tend to prefer normalizations. Then, we're going to try to build, to train, and evaluate our model. This is an example of it, of these 3 steps. Let's see this in detail. You remember the schema here that represents only 1 neuron? This code represents exactly this. So the first step is either to construct your deep neural network or to use or import a pre-trained one. It depends on the problem that you are working on. If you are working on transfer learning and you have already pre-trained model, you're going to use the pre-trained model. But here, just to give you an idea, we're going to try to construct our model. You see here, it's only 1 layer with 1 neuron. It represents exactly this schema. Then you're going to compile your model, which means prepare it to be used with the data. Here, 3 most important parameters that you're going to have. You're going to have the loss function. You remember the cost function that you want to minimize to train? Here, it's going to be mean squared error or mean absolute error. It depends. Then you're going to have the optimizer. Which method are you going to use? Stochastic gradient descent, Adam algorithm, Lion algorithm? It depends. And finally, matrix, which allows us to evaluate our model at the end. We are using the same thing, mean absolute error. Then you're going to train it using model.fit. Here, the most important part is epochs, as you can see. How many times the model will go through the whole data. And finally, you're going to evaluate it using this matrix, mean absolute error. This is a small example of 1 neuron. Now, these are the most common architecture of regression. If you are building something for the price of this house, you're going to have 3 features, so the input is going to be equal to 3. This is a big one, so you can see that we are using 3 hidden layers with 100 neurons for each. The most important parameters here for regression are the loss function, which is mean squared error or mean absolute error. And the optimizer, either stochastic gradient descent or Adam, as you can see. This is a common architecture of a regression problem. Now, this architecture can be either a small one with 2 hidden layers, like this one, or deeper one with hundreds of hidden layers with hundreds of neurons. Again, depending on the problem that you're working on and the data that you have. Here, another example of architecture of classification one. You can see that it's kind of similar to the regression one. Here we are using for the classification images, so you're gonna see that input shape is equal to the size of the image with the color channel. But the most important parameters, you can see that it's related to loss function. If you are working with binary classification, it's gonna be binary cross entropy. And if you are working with multi-class classification, it's gonna be using categorical cross entropy. And for the output activation, same thing, sigmoid for binary classification and softmax for multi-class classification. This is an example of an architecture of for classification. Sorry. Again, can be a simple one or deeper one. Depends on the problem and the size of the data. And finally, the most advanced one and complicated one, which is convolutional neural network. Again, you can see it as similar artificial neural network, but you're gonna use what we call a convolutional layer. What does it mean? You're gonna add another illustration of it. Add a lot of filters to your image in order to capture the textures, the edges of your images, in order to get some information from it. So you're gonna test a lot of filters. We call this the convolutional layers. Then you're gonna use what we call max pooling, just to reduce the size of the image. You can see it as this. You start with image, 32 by 32, and 3-channel. You're gonna put a lot of filters here, and then max pooling to reduce the size into 16 by 16, and do it again and again in order to make it very deep. And then you flatten this as a layer, and you're gonna use your common fully connected layer. This is an idea of convolutional neural networks. These are the most common one, used one. ResNet, EfficientNet, MobileNet. We're gonna try to use this, but they are pre-trained models, so we're gonna use them for transfer learning. Then, next step is to try to improve your model, right? And fine-tune it. This is an example of how to go from a smaller model to a larger model. First thing, you can see one hidden layer with one neuron. How to improve it? Adding more layers, as you can see. We are providing 3 layers here. Increasing the number of hidden units, which means the neurons from 1 to 100. Changing the activation functions. By default, it's a linear one. Here we are changing it into rectified linear unit. It can be also sigmoid or others. Changing the learning rate and the optimization functions from stochastic gradient descent to Adam algorithm, and you can play with the learning rate. And finally, fitting and training this on more data and for longer. This is how you can improve your model. Again, we want to avoid overfitting. You remember the student that learned from final exam? There is a leak between the final exam. Professor gave them this. He didn't know and learned anything. He's just doing memorization. This is exactly what you want to avoid again. We want to avoid memorization. We want our model to be as much as possible general. So we are looking for the optimal fit in here. There are some methods to do this. For example, getting more data and the better quality of the data, which is very hard and very difficult when you are working on real data to get more samples and data. You can use, if you are able to, transfer learning, but it depends on the problem that you're working on. Is there a pre-trained model or not in your field? And finally, you can do what we call data augmentation, which means you're going to take your image, for example, here, and try to manipulate it from different perspectives, for example. You're going to try to rotate it, shift it, zoom in it, in order to make it as much as possible difficult for your model to not memorize. This is the idea behind this. Try to make it as much as possible general. Then, some helpful tips. Most important part, the most concept in machine learning, same thing for deep learning. The 3 set. You're gonna need to split your data into training set, validation, and test. We want our model to be performing very well on data it hasn't seen before. This is the same concept for machine learning and deep learning. Then you need to visualize. You're going to see this. You need to visualize each step, your data, your model, your training curves, and the prediction, of course. And finally, experimentation. You need to experiment by yourself. You're going to see that by trying to resolve a small problem, you're going to experiment a lot of neural network just to resolve this. Experimentation is have a very big weight when you are working on machine learning and deep learning. Quick side, for Arabic audience, for the Arabic and for YouTube, I've already covered all these workshops in Arabic. You're gonna find all the materials, Jupyter Notebooks in Arabic also, and you can follow with me with a recorded video in Arabic. And that's it. Thank you, thank you. Now we're gonna start modeling and playing with the code. And we're gonna take 1 minute, just some feedback, and we're gonna start. 1 minute. It's gonna take you 2 seconds, just to click. All right, can start. I'll just let you, everyone get the QR code. Okay. Have your microphone, it's working, okay. I don't know, just in case. All right, now we're going to try to cover these 3 problems using neural networks: regression, classification, and computer vision. Again, you can either follow with me directly, or all the materials, you can find them in the GitHub repository. You can go to my GitHub repository, you can find all the Jupyter notebooks. And you can practice in parallel with me, or just follow the different, and you're gonna practice by your own layer. If you wanna practice right now and test, you're gonna need to go through the IBEX, the cluster here. I don't know if you are familiar with it or not, but this is the different step that you need to do. SSH into your glogin, and then you're gonna ask git clone and ask for the resources for 1 GPU, for example. And you can practice with me. But again, you can do it later by your own and follow just what I'm gonna show you. You can find also the Etherpad here, where you can, let me just get back, put whatever question you want, and my colleague Didi here gonna be happy to help you on it, right? You can put whatever you want, ask question, and you're gonna reply for it. Perfect. Let's start with the first example, regression using neural networks. Let me just make this bigger. This, okay? All right, so the idea here is to cover all these different steps that we have seen for regression using neural network. For that, for this example, we're gonna start by synthetic data first, and then we're gonna see a small example of real world. Let's start with synthetic data. Again, this is the most common architecture of regression of neural networks. We're gonna start by importing some libraries, and we're gonna create our synthetic data, which is just a linear function. And you're gonna see that deep learning gonna struggle resolving this. It's easy for us. It's just y equal to x plus 10, all right? You're gonna see that it's very, very difficult for the deep learning and neural networks to resolve this kind of stuff. Let's see this. Again, you remember the shape, it's equal to 3 when you are working to predict the price house. Here, instead of using 3 to predict 1, In our case, we're going to use one input to predict one. So 1x to predict 1y. This is why it's very difficult for neural networks, because he loves big data. All right. So as you can see, the shape of the input for the house, but in our case, is different. It's 1 to give 1. Now, we're going to start by building this neural network. Again, the architecture, we know it now. It's creating your model, compile it, and fit it. This is the most steps that you're going to find each time. So we're going to create our model, like this one. And we're going to create only one hidden layer with one neuron. We're going to put SGD as optimizer, mean absolute error for the error, and for the matrix also to evaluate it. And we're going to run this for 5 epochs. Let's see how we're going to perform. All right, we can see it from just the mean absolute, it's equal to 8, which is not great. Let's test it by predicting on the number 17. Now we know the function. It's y equal x plus 10. So if we want to predict something for 17, it should be 27. Here, the result is 24. Okay, this is not good. So we have seen how to improve our model, right? Let's try to improve this one neuron and see how we're going to perform, for example. Let's create the same one, but this time, maybe he didn't have time to learn. We gave him only 5 epochs. Let's try to give him 100 epoch. I think it's a lot. Should be okay, right? Let's see how he's going to perform. Let's see for the prediction. Okay, 30. Not that good, right? We gave him 100 epochs, he didn't improve anything. Okay, what I want to show you here is that when you're going to start working with deep learning, this is the steps that you're going to always do. Build, evaluate, tweak, again and again and again. This is the idea. Now let's try maybe to visualize everything, because now we get only numbers. Let's try to see what's going on. For that, you're going to build a bigger model, bigger samples. So we're going to use same thing, same function, but this time using 50 samples. Okay, it's good. Let's see how we can use these 50 samples to create our deep learning model on it. First thing, you need to split your data into training and test, right? Same thing every time. So for that, we have 50 samples. We're going to take 80% for training and 20 for test. So we have 40 to train on and 10 to test on it. If you visualize this, it's going to give us something like this one. Okay? So he's going to train on the blue one here, the samples here, in order to predict and to be tested on this green. This is the idea. All right, let's start by the same model. 1 neurons, 100 epochs. Let's see how he's going to perform. Okay, just by looking to the mean absolute error, I have an idea, but let's move on. If you look at to the model that you are using, you can use model.summary. Here you can see that the trainable parameters are equal to 2. Why? You remember this schema? This is exactly what you have built right now. One hidden layer with 1 neurons. This is why you get only 2 trainable parameters, W and B. If we used 2 neurons, you're going to have 4 trainable parameters. All right. Now, let's try to visualize this prediction to get a better idea. This is why I'm telling you, try always to visualize. Okay, now I will predict using my model. It's going to give me numbers, but let's visualize them. All right, now I have a better idea how it's performing. You see, he's struggling with the linear function, which is nothing. In red is the prediction, but we want to be exactly this. But this is the prediction. Okay, let's try now to evaluate them using the metrics that you have already seen, mean absolute error and mean squared error. Again, if you use model.evaluate, it's going to give you the mean absolute error. And if you can also use mean squared error, as you can see. Let's build a function for them to make it easy for us to evaluate our models layer. This is a function that's going to allow us to measure the mean absolute error and mean squared error between the prediction and the test. And now let's try to improve this model that is struggling on a linear function. We're going to test this. First model, 1 layer, 1 neurons, 100 epoch. Then you're going to try another model, 2 layers this time, 100 epochs. Third model, 2 layers, 500 epochs. And the final one, 3 layers with a lot of neurons for 150 epochs. Let's see if we can resolve these linear functions or not. Let's see. We have already seen the first one, 1 neurons with 100 epoch. Okay, you can see how he's performing. Very bad. This is not good at all. And if you evaluate it, you can see that the mean absolute error is 30 here. Okay, big. Now let's try the second model, this time using 2 layers. Let's see if we can improve it or not. 2 layers with 1 neurons. Okay. A little bit better, right? Okay, we have an idea. Maybe now, by using the same model, maybe by letting him train for 500 epochs, we're going to get a better score. Maybe. Let's try this. I mean, I like it. It's improving. Let's do exactly the same thing. Same model, but this time with 500 epochs. Is he going to be able to improve or not? Let's see. You can see that it starts taking time. Again, I'm using IBEX here, A100 GPU. You can see it's taking some time. This is why. Okay. Worse. Why? I mean, here, this is an example of overfitting. He starts memorizing things by his own. This is why it's getting even worse. It's overfitting here. So there are techniques to avoid this, of course, like early stopping or maybe adding more layers specific to overfitting. But this is just an example of, I want to show you that the model starts memorizing and not getting the right patterns. Okay. Now let's start and finish with final most advanced one, which is 3 hidden layers, 400 neurons, 100 neurons here and 100 neurons here. We're going to change the optimization function. You remember we were using stochastic gradient descent. Now we're going to use another algorithm, an advanced one, Adam algorithm. I'm going to use it for 150 epochs. Let's see how we're going to perform. It's a bigger one, you can see. Let's see if you're going to be able to resolve this linear function, which is very simple for us. Okay. All right, finish. Amazing, almost perfect. The error is 0, almost. But again, in order to resolve this, you see, what model did we try to do just to resolve a linear function? Why I'm showing you this? Because first, 2 things. Deep learning loves big data. This is the first thing. Now, we don't have a lot of samples. Second thing, you remember the rule that said, if you have already simple rule-based systems that works, go for it, forget about it. This is the kind of stuff. I mean, it's a linear function. We know how to resolve it. Don't use deep learning for this kind of stuff. It's a waste of time and resources. Go for your model, like the mathematical one that you know the system behind this. This is an example of it. And you have seen that it took him a lot to just resolve this linear function. And you can see the difference between the different models. All right. Now, again, you can save this model using model.save and load it again. This is very important when you are working with big data, to always save your model and load it again. As you can see here, you can load it. And now let's start working on a large example. a real world example. Here, we're going to try to work on the cost of the medical insurance of individuals based on these parameters: the age, the sex, the BMI, children, and smoking status. So for that, we have CSV files. It's called insurance.csv. Again, all the materials, you're going to find them in the GitHub if you're on a practice layer, even the data. So here, we have our data frame that looks like this one: age, sex, BMI, children, smoker region, and the charges. Again, you remember in the previous course, we need to do some stuff on the categorical features. We have numerical like the age and BMI and children, but we have also categorical features: sex, smoker, and region. We need to convert them into something neural networks can understand: numbers. You need to convert the categorical features to numbers. All right. So if you look at the info, you can see that we have objects that represent string here, and the numbers, float and integer. So the first thing, you're going to use Panda to convert these categorical features. We have already seen this, get dummies. Just by using this function, get dummies, it's going to convert all our categorical features into something numerical, one hot encoder. You remember? This is it. OK, now we have our data frame all in numerical. Second thing is to split it into features and labels, the target variable that you want to predict. So x and y. For that, we're going to predict these charges. So we're going to drop it. And we're going to keep only x that's going to represent only our features. And y is going to be representing the charge that you want to predict here. OK? So we have our x and y, features and target variable, y labels. Second thing is to split it into something for training and test. Again, scikit-learn make it easy. It gave us this function, train, test, split. So we're going to take 80% for training and 20 for test here. OK, so we have our x-train and x-test, as you can see. And let's start building these neural networks using this pre-processed data. Again, let's start by using 2 hidden layers with 1 neurons for 100 epochs. Let's see how it's going to perform. OK. I can see it. It's already very big. OK. We are around 6,000 for mean absolute error. It's very big. How we can improve it? OK, let's try these 3 things. Increasing the number to 3 layers, increasing the numbers of neuron unit, and changing the SGD to Adam. We have already seen this. Maybe it's going to perform better. Let's see. OK. And you can see how it's going to take time each time. All right, 5,000. OK, good enough. We improve it. Now, let's look at the curve. This is why I told you, like, always visualize. Let's look at the loss function. What's going on? OK, just by looking at the loss function and mean absolute error, you can see that it's still decreasing. Maybe if I'm going to add some epochs, it's going to get a better score. OK, from this, I can see it. You see? Let's add same model, 100 epoch. How? Just you're going to take your model and add another training and epochs. And it's going to understand that you want to add more epochs to your trained model. OK, let's see how it performs. When I added, amazing. We gain more than 30% decrease in error from how it was, 5,000 into 3,500 for mean absolute error, just by adding 100 epochs. Amazing. But if you look at the loss function now, I can see that it starts to stagnate. So adding more epochs doesn't make any difference here. Now we have seen also, and I talked in the presentation, that neural networks prefer and tend to be working more better when you are normalizing your data. Let's do this and see if it's going to give us any difference by normalizing our data. As you can see, if you take the medical insurance here, you can see that we have different columns here, numerical one, and we're going to try to normalize in them. We have seen this with min-max scalar. So we're going to use this make column transformer, which going to normalize these features, the age, BMI, and children, and which going to do the one hot encoder for the other categorical features. So we create a function that's going to do both at the same time. Okay, then you're going to create your X and Y, split your data, and normalize it by doing transform. Okay, now we have normalized our data. This is an example of it. This is how it was before, and this is how it comes. All numerical and normalized. And let's see how our model is going to be performing. We're going to take the same one as before, but this time we're going to apply it to normalized data. And let's compare it to the previous one. So 3 layers to 100 neurons, 10 neurons, and 1. Okay, perfect. We gain, again, 10% by reducing the error. Amazing. Again, always when you are working with data, normalize them each time. You don't care. Normalize everything. He loves normalization. Don't forget to do it. Now, let's finish with the big advanced one. As you can see here, we're going to use a very big one, an advanced one, 256 neurons. And we're going to add a new one, dropout, new layers. These layers going to allow us to avoid overfitting. So you can increase and put a lot of layers, but each time don't forget to add this dropout to reduce the overfitting. That way your neural network's not going to memorize everything. And we're going to use a new optimization algorithm, Lion. It's an advanced one, better than Adam. And let's see how we're going to perform. Okay? And we're going to do it for 250 here, for example, epochs. Let's see the performance. Again, it's always taking time when you're working with neural networks. Keep this in mind. Even using A100 here, the most advanced GPU for the moment in iBooks. Perfect. You see, we get 50% less. Amazing. From 3,000 to 1,600. Now, you can always look at the different metrics here before we finish, as you can see. And you're going to see that 1,000 for mean absolute error is very big. Not really, because if you are looking to the charges that you are working with, it's huge numbers. You are trying to predict 60,000, for example, dollar. So 1,000, it's okay. It's just 12% far from the mean. And same, if you look at the R2 score, this is why it's very high, the variance. 0.86, so it's amazing. You build a very good model here, for example, that predict the insurance charge. And you can see the prediction. Compare it to the actual value. Best fit is in red. And you can see that these are the most difficult one to predict, as you can see. And residual, it should be equal to 0. This is an example of how you can resolve a regression problem using neural networks. Again, I'm putting you a lot of exercise to exercise by yourself, put you a lot of Jupyter notebooks. So get back to the GitHub repository and can practice by yourself. Now, before we're gonna move to the next one, just wanna show you something. Remember, I told you like, when you start working with the neural networks, GPUs are important. Just to show you something, if you look at the memory of my GPU, you can see that it's already full. It's A100. It has 84 gigabyte for VRAM, and it's already full. You can see it here from the GPU memory. I mean, if you look at this, you see, it's taking all the memory. So you can't not even go to the next one without doing a reset for the kernel and empty this memory. This is why GPUs are very important, but you should be careful when we are working with big deep learning models. All right, now before we move to the next one, let's take a break, 10, 15 minutes, and then let's see the two other examples of classification and computer vision. All right, now we have seen regression, right? Let's move on and see how we can resolve classification this time using neural networks. Again, same idea. We're going to start with synthetic data and then move on to some real data. Okay? Let's start by building our synthetic data. We're going to use for this a function called make circles. Okay? We're going to create 1,000 samples, as you can see. So we're going to have our x and y. So x, the features, y, the labels, the target variable, the label that we want to predict. Okay? X looks like this one. In our case, it's going to represent coordinates. How I know this? Again, always look at your data. Visualize them. This is the data frame that you're going to try to resolve. So you're going to have, for label 1, so class 1, 500 samples, and for class 0, 500 samples. And if you look at the data, it's this. It looks like this one. And you're going to want to do neural networks on this in order to make it its classification problem, right? We're going to try to predict the samples in blue and in red. Let's try to resolve this problem. Let's start by, again, building a small neural networks and see how it's going to perform. We have our input, as you can see, 1,000 samples, 2 coordinate, so it's going to represent the features, in our case, 2 features, to predict 1 label. This is an example of 1 sample, coordinate, and the label. And let's start doing this, same as before. But you're going to notice that now we are working with binary classification, right? 2 class, 0 or 1. For that, we're going to use, before we were using mean absolute error or mean squared error for the loss function. Now we're going to use what we call binary cross entropy, because there is only 2 classes. And the metric is going to be different, because we are working on classification problems. So we're going to use accuracy. OK, let's build this for 5 epochs. See how it goes. OK, you can see that 50% accuracy. Let's evaluate it. It's 50%, which means the algorithm and neural network is doing as good as guessing, 50%. This is not good. Let's train it for 200 epoch. Maybe by adding a lot of epochs, you're going to be able to get the result. Even with more than 200 epochs, still guessing. Accuracy, it's equal to 0, almost 5. This is not good. What you can do, again, maybe adding a new layer. Let's try and see how it's going to perform. I'm going to add another layer, make it a little bit complex, like add some complexity to my neural network. Is he going to be able to get burst score or not? Still, 0.5. Why? Why I'm getting this? Why still the accuracy is good as guessing? Now, again, we have seen this. You can always go and make a bigger model to improve it. These are the different steps, right? Let's try to build a complex one, a very big one. And let's see if you're going to be able to maybe resolve this, why I'm getting only 0.5. I'm going to use 3 layers, 100 neurons for the first layer, 10 for the second. I'm going to use, we have seen this, Adam is very good, better than SGD, for 100 epoch. Now, I should have something better than 0.5, 50% accuracy, right? But again, from what I see, it's still worse, nothing, same, 0.4. Why? This is why it's very important to look to your data always and to your model. If we look at our model and see the prediction, we're going to see that what he's doing is a linear separation. Now I get why I'm always getting 0.5, 50%. This is why it's important always to look at your data and the model, what he's doing. He's doing a linear separation, but our problem is that our samples are non-linear. So what we are missing is the non-linearity. Okay, now I get it. This is a small website that allows you to visualize your model. This is very good to visualize this. Let's see this. You can go here, TensorFlow Playground, and you're going to see that you can build your architecture. Now you can visualize better. This is what we are doing, only x1, x2, so the samples, and you have 1 neurons. And if we play this, you're going to see that we get 0.5. Same thing as we are getting, because it's linear here. Same thing. If we do, okay, same thing, 0.5. You get the idea? This is a better way of looking at your neurons. Okay, now what you're going to try to do, you remember the activation functions? By default, it's linear. This is why we are getting 0.5. By default, is using this, linear. If we do this, we're still going to get 0.5, as you can see. Because by default, it's using linear function. The idea here is to try to play with it and to make it, you can see, it's doing linear separation. To change it, like this one, for example. 2 neurons with rectified linear function. Is he going to get a better score? Still not, as you can see, 0.5, same thing. We can do this here, build exactly the same architecture. So we have 2 neurons with rectified. And you are obtaining the same results. So what you are missing? What you are missing is the output functions. Remember when I told you that when you are working with binary classification, you need to use sigmoid for the output function? This is what you are missing. So if we want to build this example here, we're going to use 4 neurons. But for the output, I'm going to use sigmoid this time. Let's see how we're going to perform here. 4 neurons, but instead of using rectified, I'm going to use sigmoid. Perfect. Now he got it. You see? Now he's able to resolve it. And again, this architecture, it's exactly the same as this one. 4 neurons, and 1 for the output, sigmoid. Let's see if you're going to get a similar score or not. Okay, 150 epochs. Okay, perfect. 97. Now we get similar results as here. This is what we were missing, no linearity. Amazing. Now we know how to resolve this kind of classification problem, right? Next thing to do, just to give you an idea about these activation functions. Before, when we were working on linear function, he didn't do anything. Like the input is similar to the output. He's not doing anything. He's not manipulating your data. But if you look at this is, for example, your input. If you're going to use sigmoid, this is what he's going to have as a result. He's going to do some manipulation into your data. This is where he's gonna learn the patterns. Before, he was doing a linear function. The input is similar at the output. He's not learning anything. So this is just to give you an idea. Similar thing for rectified linear. The output gonna be looking like this one. So by manipulating the output, he's learning these patterns. This is why it's important. All right, now we can create our model to evaluate it. So we have 50 samples. We're gonna use training set, test set each time. 80% for the training and 20% for the test. And let's see if you're gonna be able to resolve this. So again, we're gonna use this model, the same one. So we're gonna use 800 to train on and 200 to test. Let's see how we're gonna perform. Okay, amazing. You can see 99% on the training, because this is the training here. 200 epochs, perfect. Almost 100, you see? If you look at to the test, you can see the accuracy is 99%. Amazing. He knows how to separate these two classes now. We get it. And if you look at to the data, this is how it looks like. This one? No, because the test is performing very well also. If he wasn't able to perform very well on the test data, now it becomes overfitting. He's memorizing the things. This is the difference. You need to always look at the training and the test. Now he's performing very well on the test, as you can see, 99%. All right, you know how to separate this. This is an example of how to separate this. Now, always look at to the curves. This is what I was talking about, the loss curves. History, make it easy to us. It's going to give you the accuracy and the loss for your training. And when you look at to this, you're going to see that it's something like this. We want to always our accuracy to be high and the loss to be very low. This is an ideal graph here. As you can see, this is the ideal curves. You're not going to get this all the time. This is the ideal case. Now, sometimes when you are working with big data, the problem is that it's going to take you a lot of time and a lot of resources. To reduce this, we're going to try to look at for the best learning rate, which means it's going to allow us to accelerate this learning and converge quickly to final results. How we can do this, how we get the best learning rate? Again, there is a function for that, learning rate scheduler. You're going to test a lot of learning rates in the beginning for your model. I'm not going to run this, it's going to take time. And at the end, it's going to give you some curves like this, accuracy, loss, and learning rate. And if you look at to learning rate versus loss, it's going to give you something like this one. Let me just put it like this. And what we want to do is looking for the best learning rate that gave us from the beginning the minimum loss. Here, where we can choose the best learning rate, as you can see, because this is learning rate versus the loss between 0.01 and 0.1. This is where the ideal learning rate is. And just by taking this value for the learning rate, you're going to see that you're going to obtain and get the same results, but this time just by running 25 epochs. Let's do this. Before, we were using 200 epochs to get this 99%. Here, just by running 25, I'm able to get the similar results, 99 accuracy. You see? So always look for the ideal learning rate. It's going to allow you to accelerate the convergence of your model. All right. Now you can evaluate it using these different metrics. Again, we have seen this, accuracy, precision, recall. And this is an example of confusion matrix. As you can see, confusion matrix is going to represent Let me reduce this. Between the difference between true labels and predicted labels. And here you're going to have what we call the true positive and true negative. And here, the false positives and false negatives. And this is very important when you are working with classification problem. You're going to see this in the real data. So we have confusion matrix, a function. But again, if you want to apply it directly, it's going to give you an error. Why? Because you remember, your model is giving you probabilities as prediction, not the labels directly when you are going to use model.predict. So for that, don't forget, the prediction is going to be probabilities. Don't forget to convert it into something a model can understand and compare on. Labels, 0 or 1. For that, just take the round, because we are working with binary classification. More than the 0.5, it's class 1. Under 0.5, it's class 0. Now I can create my confusion matrix, as you can see. And I have only 2 samples where the model got wrong. And we have seen this. Maybe this 2 here. I don't know. Where is this 2? Maybe this one and another one. This is what it gives you, the confusion matrix. Number of samples that you get wrong. All right? Now let's try to work with a larger example and real data. We call this the fashion MNIST data. You remember in the first course, we were working with MNIST data with 60 or 70,000 images for 10 classes of digit number from 0 to 9, right? 10 classes. Now we're going to use similar data, but this time for clothes. Let's look at this data, how it looks like. So we're going to have a lot of images that represent 10 classes. If you look at this training data and training labels, you're going to see that it's matrix. Of course, the image is a matrix going from 0 to 255, the authenticity of the pixels. But here, our training is going to be 60,000 images of the size of 28 by 28. And we're going to use 10K for the test, as you can see. 10K for the test. And training, we're going to use 60,000. And we have 10 classes. So for each class, we're going to give 6,000 for training and 1,000 for testing. OK, we know how to separate our data. It's already done. And let's look at these images. OK, it looks like this, clothes. OK, but if you look at the labels, you're going to see that it's from 0 to 9. OK, I know my data. So I know that from the GitHub, these are the true class names. So I'm going to use the class names for better interpretation. And now I can have something like this one. OK, this data that I'm going to work with. And this is some classes, T-shirt, for example. Let's look at the others. We're going to find pullover, back, other random, sandal, back. Now I have an idea about the images that I'm going to work with. OK, I have 10 classes of images. I want to predict and do resolve a multi-class classification problem using neural networks. So let's start by building our first model on this. The difference, you remember, before, for binary classification, we were using for the output sigmoid because we were working on binary classification, 0 or 1. Now we are working with 10 classes. Don't forget to use softmax this time. Others are going to be the same metric accuracy, the same optimizer, but for the loss, it's going to be different. It's not going to be binary cross entropy, but this time sparse categorical cross entropy. OK, perfect. Let's build our model and see how it's going to perform. On this, you can see for 10 epochs, the validation accuracy is very low here, 0.29, OK. 38, it's improving. Now again, don't forget, you are using artificial neural networks to resolve a multi-class classification problem for images. Don't forget this, because at the end I'm going to show you something. Okay, you can see that not that good, huh? It's 50% for 10 classes. Okay, it's better than guessing, because guessing for 10 classes is equal to 10%. But again, it's not that good. And if you look at the summary, you can see that we are using already 3,000 training parameters. Okay, you remember I told you, try always to normalize your data. Don't forget this. Even if you are working with images, any kind of data, normalize it. Okay, I know that the intensity of my image go from 0 to 255. Let's normalize it and divide all my data by 255. That way it becomes between 0 and 1. And let's run the same model on this normalized data. And let's see how he's going to perform. Amazing. From just the first epoch, we get a better score. 0.67, okay. All right. 0.7, just by normalizing the data. This is why it's very important. Don't forget it. You see how he's performing? 75%, okay, for 10 classes, which is okay. Let's see final epoch. Okay. You see, just by normalizing the data, we get an improvement of from 0.45 to an accuracy of 0.75. Don't forget to normalize the data. This is very important. And this is how it was before non-normalized data and after normalizing it. This is what you are looking for. This is to go low for the loss for the training and the validation, and this is to go high on the validation and training. This is the kind of figures that you are looking for. All right, now let's do exactly the same thing, looking to the best learning rate, right? Each time, do this. So here, we're going to use the same function, as you can see. I'm not going to run this again, because it's going to take a long time. So this is the kind of curve that you're going to have. And you can see that the ideal learning rate is here. You can see it. 0.001, for example. So if you run this just for 20 epochs this time, you're going to see that we're going to get similar results or even better, as you can see here. So look always for the best learning rate. Don't forget this. And let's run the final advanced model here. A very big one, as you can see. It's got a lot of layers, as you can see. A lot of neurons, 128, 256, 500 here. Adding some dropout, we have seen that in order to avoid our overfitting, we need to add this dropout layer, which gonna just drop 20% of your data in order to make it harder for the model to not memorize each time your data very good. And let's see how we're gonna perform. This is the advanced one. Let's see. You shouldn't have.
Is 20 constant?
Which one? 20 epochs, because we have seen that.
0.2 at dropout.
No, it depends. It depends. It's by experience. We remove 20% of the data each time, each layer. But no, you can always add more by experience, like by experimenting a lot of it. But by default, in general, we are taking 0.2. This is the common one. It's like the random state, 42. But again, you can always try by yourself. This is the idea. But again, this is an architecture of a network, very known one. This is why I'm using it. Yeah.
Shutting down neurons in the layer. So if you go to 0.5, it means that half of your layers.
Yeah.
Which is good.
Depends.
It doesn't memorize now.
Yeah, but it depends. Maybe it's not get enough information when you're gonna drop 0.5. It's not able to predict anything. It's gonna be lost.
Depending on the complexity of the data,
Yeah.
you need to find a balance.
The balance, exactly. 0.2, it's okay. It's okay. Between each layer, as you can see. Now, amazing. 0.87 with the advanced one. Now you are happy, right? You got 0.87 with this advanced neural network. But if you look at the summary of the model, you can see that he used 400,000 parameter to get these results. And you have seen that it took him a lot of time, right? You can always save it, load it again, as this, for example. But if you look at the confusion matrix, this is why it's very important, because you are trying to predict 10 classes. Always look at your confusion matrix. It's going to give you some insight, what's going on behind this. Okay, we get 87% accuracy. Amazing. Let's look at the confusion matrix. It looks like this one. If you look at this, it's going to give you some insight. Why? If you look at this t-shirt class here, he got 81% right and wrong 13%. Why? If you look at where he got wrong, you're going to see that, shirt. Makes sense. He's confusing t-shirt with shirt, right? Same for shirt. You can see that he got confused with t-shirt with 11%. Why it's important? It's going to give you some insight when you're going to present this and justify what is going on with your model, why he's not performing very well. Look at always the confusion matrix when you are working with multi-class classification. It's going to give you the idea why he's confusing. And for me, it makes sense. He gets confusing with t-shirt and shirt. It's very hard maybe for him, but even for me. So it's okay, you see? Now, again, let's build the prediction for this and see how we're going to perform. Okay, this is an example of function of, on the test data this time, I'm predicting using my trained model. Okay, he's confident at 98%, it's a sandal, which is true. Perfect, let's try another one. Confident with 72%. Again, I told you, it's probabilities that it's a coat. Okay, he's performing very well, right? Amazing. Moreover, again, he got it right. This data, it hasn't seen before. The model hasn't seen this. This is the test data. So you can see that 87% is very good. It's performing very well on 10 classes. Now, you remember, I told you, we're working with artificial neural network with images. But if you remember, we were talking about convolutional neural network, which is optimized for working with images. Why? Let's see in a small example. This is a sneak peek just to show you, just by using a convolutional neural network this time, not artificial neural network, as you can see here. I'm going to use the same data. Let's run it for 10 epochs this time. And you're going to see how it's going to perform. And the speed of the convolutional network compared to the other one, which took us a long time to do. Let's see. You see? See how fast it is? How he's manipulating very good the images? And the accuracy is 90% just for 10 epochs. This is why convolutional network is very, very good for images when you are working with images. This is the difference. It was very fast. It's optimized with this kind of data. All right, let's see the final. Again, putting you a lot of exercise that you can play with it in the GitHub for each example. And now let's move on to the last example, which is convolutional neural network for computer vision. Again, it means working with images, computer vision. Okay, so for that, you're going to download this. You're going to start with binary classification this time with images that represent pizza or steak. I'm going to try to build a classifier for this. Let's see this. This is how the data looks like. This is the architecture that you need to do each time when you are working with images. 2 folders, train and test. Then you're gonna put your classes. Here, we are using binary classification, so pizza and stack. And then you're gonna put all your images. This is the structure that you need to do each time when you are working with images. And classification, of course. So let's look at the data. I already downloaded it. Okay, so I have my 2 folder, test and train, and for each one, I'm gonna have 2 folders, pizza and stack. A lot of images. If you look at the directories, you're gonna find that we have 750 images for training, and we're gonna use 250 for test. Okay, that's not a lot, but let's try how a convolutional network is going to be able to produce with these 2 images. Okay. If you look at the data, it looks like this one. You can see the different shape. Here it's 500 by 500. But you can see that they are different shapes. They are not all similar for the pizza, you can see. Okay, now you have an idea about this. And you can see the different shapes. First thing to do, always, normalizing your data each time. So we're gonna divide this by 255. And we're gonna use a common architecture. It's called TinyVGG. And it looks like this. Now, a good website that I like, and to explain this, very good, this architecture, is this one, CNN Explainer. Let's take a look to it. This one. This is exactly representing this architecture. You're gonna have convolutional layer, max pooling, then convolutional layer, same max pooling, you flatten everything, and then you produce the output. This is exactly what's going on behind this. You're gonna have your images, right? The color channel, RGB. First thing that you need to do is to do a convolutional layer, right? Here, he's gonna test a lot of filters. Let me zoom. Test a lot of filters here for each images. Then, next step is to use the activation function. Here, it's rectified linear unit. What he's doing is just taking the max between 0 and the pixel intensity after filtering using the convolutional layer, as you can see. Okay? Then, same thing. We have seen in TinyVGG. Convolutional layer, another one, you're gonna do exactly the same thing. Take the output and do a lot of filters that goes through the whole images to capture some information, maybe the edges, the textures. It depends on the filters that you are working on.
This is normally used for the images. However, it's not the case for the
Yeah.
time series data, right?
Time series, no. There are other, no. Yeah, exactly. Time series, you should use, not always. You can use some deep learning like LSTM, GRU. Transformers work the best on time series. But this is advanced. This is just introduction. So, convolutional network, remember, using it only for images. Can be used for other problems, but they are optimized with images. Time series data, different problem.
For data, what do you use? If you want to find correlation between data.
For what?
For correlation.
Here the
Correct.
question is, what
Yeah.
format of the data? Because, for example, here
Yeah.
we're talking about images. That can be divided in 2 channels, red, blue, green.
Yeah,
If you're talking about, yeah, but if you're talking about a tabular data, like we have Excel sheets,
yes,
then machine learning, the previous
Yeah.
one is the best tool.
even for correlation.
Even for correlation,
Yeah.
because it will give you actually access to the correlation between the different features after
Exactly.
training the model. Based on feature importance or the shape techniques
Yeah.
So in this case, deep learning excels at
Images.
because it's a highly condensed matrices, a lot of matrices as a matter of fact.
Exactly.
They can be composed in different forms. And this is why this is the explainer trying to teach what is each of the layers looking at the corresponding matrix. And then we have the
Filter.
different colors there and shapes.
Since the image is the only use case I can see, right? Image classification is the
Or
only to use
for
case.
convolution and neural networks, yes.
Yeah.
Com-
I mean, the
graph-
best case, yeah, exactly.
graph
You can
neural
use,
networks,
yeah,
there's another kind of neural networks.
yeah,
Graph neural networks are different things that can be applied for atomic relationships, or even relationships among a graph, a literal graph with nodes and edges. Like, for example, atom representations. Or
All representation of data
That
is
is-
factorial design.
there is relationship somehow.
Ah.
related
Yeah.
somehow.
but again, this is why I told you, like, this is optimized for unstructured data. Deep learning is very good with images, text, audio files. This is where he's gonna perform the best. In your case, if you are working with CSV files and Excels or tabular data, the machine learning course, the first one, we have seen examples where models like GBDT, gradient boosted algorithm, like XGBoost, like GBM, CatBoost, these one are gonna be performing the best with your kind of stuff using CSV files.
So, part of deep learning or machine learning, that's also confusing because some people use TensorFlow for machine learning data.
TensorFlow for? There is no machine learning data. There is data. And then you're going to apply either machine learning algorithm on it or deep learning algorithm on it. Depends on the problem that you're working on. But there is only data. It depends on the data that you have. Is it tabular data, structured data, like CSV files, Excel files,
Yeah, that's
or
what I'm talking about. Excel files.
Excel files? Okay, it's deep. We call this tabular data or structured data. Here, the machine learning algorithm tends to be working the best. You can always apply, as we have seen in the CSV file for regression, deep learning, neural networks. Is it gonna perform better? It's your choice. You need to try. But I told you it's not a rule. By experience, machine learning algorithm tends to be working the best with tabular data. Got it? All right. So this is the idea about tiny VGG. Again, you're gonna do convolutional layers to capture some information about textures, edges. Then you're gonna do max pooling. Max pooling is just to reduce the size of the image, going from 60 to 30 by 30, as you can see. He's taking the max between these pixel intensity each time. It's gonna reduce the size of the image and also the size of your neural network. And you're gonna repeat this. So convolutional layer, max pooling. Convolutional layer, max pooling. And then he's gonna predict at the end if it's espresso or koala or school bus, as you can see, using the softmax, the last activation functions. So this is an example of what is convolutional network and what is tiny VGG architecture looks like. All right, so this is exactly what you wanna do and build here. We're gonna build this architecture, and this is exactly how it looks like. This is the model of tiny VGG. Convolutional layer, max pooling. Convolutional layer, max pooling, and flatten everything with sigmoid because we are using two classes here, not multi-class. Let's run this and see how it's gonna perform. Now, it's becoming a little bit big for the GPU, as you can see. And it's gonna take some time. Now we are running this only 5 epochs. Okay, amazing, you see? This is not a custom architecture. It's a very known one. It's called tiny VGG. This is why it's important when you are working on your own problem to look to the most used architecture for your own problem. Now I know that when working with classification, tiny VGG is very good. for classifying images. And you can see it. Just 5 epochs, I got my 85%. Now, if you look at to the model summary, what I want to show you here, it's only, and I say it again, only 30,000 parameters trained parameters. Why I'm saying this? Because if we look at to the previous examples that we have used for the second example classification problem, we used artificial neural network. Let's take the same one and use it this time for these two class imager. Here, we call this artificial neural network, not convolutional neural network. And we're going to apply it to the same data. You're going to see that it's not performing very well, right? But another thing that I want to show you, you're going to see it. So the accuracy is 0.5. This is not good at all for 5 epochs. For TinyVGG, we got 85%. But if you look at to the model summary, you're going to see that this small one used 600,000 parameters, which is a lot compared to the convolutional neural network, which used only 30,000 parameters. You see? Now, let's take it further and use the most advanced one. You see, you remember the last one, the one with a bigger one, dropout and everything. Okay, this one gave us a very good result, right? Let's see how we're going to perform with the images. It should be good, right? It's an advanced one, as you can see, with dropout, 500 neurons. Let's see how we're going to perform compared to the convolutional neural network. First, you can see that it's taking more time than convolutional network. This is the first observation. Then, okay, we get 0.70. Good, good. You see, it's performing very good. The advanced one, 75, maybe. Okay, 77. You see, amazing. You are saying that, okay, the advanced one is producing a good result, right, compared to the convolutional one. But in reality, if you look at to the model summary, you're going to see that he's used 20 million parameters to get these kind of results. Compared to the convolutional neural network, we used only 30K, which is amazing. Why I'm telling you this? Because don't start working with models and make them very big and you are happy with it. It's not going to fit in your GPU, memory of the GPUs. This is very important. You should target always specific architecture based on the problem that you're working on. Working with images, choose the convolutional neural network. Don't use artificial neural network. Even you can see, we get almost the same result, right? But you used 20 million parameters to get this. But with convolutional network, we use only 30K. All right, now to give you an idea. Now let's break it down. So again, you can build your custom image here, as you can see. Same as before, we're going to have our images, stack and pizza, training and normalizing everything, as you can see here, rescaling it. And let's try to create a custom one that looks like TinyVGG to understand better what's going on. Same here. You have your images, which is matrix, size, width, height, and 3 channel, and the labels. Okay, now we get used to it, and let's create our model. We're going to start by a small one, as you can see, 3 convolutional layer, and the flattened one. Let's see how we're going to perform. You're going to compile it. You need to remember these steps. They are each time the same. Creating your model, compile it, fit in it, train it, and then test it to evaluate it on test data. Next step is to fit it, which means training it.
The training would be on the actual data or synthetic data?
Here, it's an actual data, real data. Images of pizza and stack, in our case here. It's a binary.
If you use a synthetic data and then make like the same model with actual data, there will be like variance in the results.
Yeah, but it depends on the data that you have. If you don't have that much data, sometimes synthetic data can help, but a good one. You need to create a very similar one to your problem. Not, yeah, exactly. It should be very, very similar to your problem and data that you want to test on it. So here, again, we're going to train our model. And let's look at to the curve. All right. Pretty good. 0.84, as you can see. 85. Okay, good. If you look at to the curve, all right, the loss function and the validation. For me, a little bit of overfitting. Why? Because the loss for the training is going down, but for the validation, it's going up. So this is not good. Let's try to rectify this. How? Let's look at to the loss curve again here for the separate one. You can see it. You see? The training is going down, but this is going up. Same for the accuracy. Accuracy is very good for the training. For the validation, not that good. Let's try to rectify this. How? Maybe, you remember, we can increase the number of convolutional neural network, add in drop layers, max pooling, you remember? Max pooling going to reduce the size, which means not memorizing all these parameters and these neurons, as you can see. Let's add the max pooling layer here, as you can see. Before we didn't use it. It's going to reduce half of the images. Let's see if it's going to improve this or not, these curves. And this is very important. Look always to the curve. It's going to give you insight of what your model is doing. Okay. Similar, almost similar accuracy, which is good. But let's look at to the model summary. Again, we have only 8,000 here. Why? Because we used max pooling. We reduced the size. If you look at the previous one, it was 400,000 parameters without the max pooling. And this is going to take a lot of in your GPU memory. So don't forget to use max pooling to reduce the overfitting thing. And if you look at to the plot, okay, better than the other. Now the validation is going down also with the training, and the accuracy is going up same. So by adding the max pooling, even if we reduce the training parameters, we rectify a little bit this overfitting. Okay. Another way of doing it is to use data augmentation. You remember? Adding and manipulating your data. For that, we're going to use the same images, but this time we're going to add some rotation, zoom in it, play with it, flip it, to make it harder for the model to memorize, because we want to avoid overfitting. This is the kind of stuff that you can do. Add in dropout or max pooling in our case, because we are working with images, and doing data augmentation to make it harder for the model. This is what we need. So here, I'm going to create a new data, augmented images that looks like this one. Let me show you. So this is an example of our original image and how it become. You see, it's become very hard for the model, which is good, because imagine you are using your phone. Maybe this is an example of how you're going to take your photo when you're moving. Try to make it very difficult to your model to be as much as possible general, to not do memorization and not like being happy with your data. I got the best model, but at the end of the day, just memorize your data. On data it hasn't seen before, is not going to perform very well. So make it from the beginning very hard for your model to be as much as possible general. And this is the kind of stuff that you need to do is data augmentation, for example. You can see how it's manipulating your data, make it very hard for it. And now we can always train it. And let's see how the curves gonna look like. So even if it's gonna be in the accuracy a little bit less than the other model, it's okay, as long as the loss curves looks very good. Because we want our model to be general. So here you can see, okay, 84, which is good. Okay. This time we are using the augmented data set. 84. So I prefer this model here than the other one, even if the accuracy of the other one is better, because this one was trained on augmented data, difficult one. So he was able to be more general than the other one. Perfect, as you can see, 84, which is good. And you can see the looks of the look of the graphs here for the loss and the train validation accuracy. This looks very good for me. Perfect. Now, this is the idea. You're gonna repeat until satisfied. You're gonna train a lot of architecture, try a lot of things, and change a lot of things. And play with it again and again and again. But at the end of the day, if you are working with classification problems for images, use transfer learning. This is very important. Use already models that has trained and pre-trained on huge data. Always use transfer learning. Why? Let's see an example. You see, we were working on that and trying our best to get our 0.84, but just by using transfer learning, TensorFlow allows us to do this. This is an example of it. So here, you can always try to play again and again and try different models. But if you use advanced one, using transfer learning, MobileNet, here it's called, and it's already pre-trained model on millions of images of hundreds of classes. It's called ImageNet. This is a huge data set. And it was already pre-trained on this. So instead of going from scratch and creating our architecture as you have seen now, this was done on purpose to show you how to create your custom model. But again, if you are working with images, use always transfer learning. It's going to save you a lot in time and in money. So here, I'm going to use MobileNet and adapt it to my problem, which is pizza or steak. Let's see how you're going to perform on 5 epochs. You're going to download the model, as you can see, and then you're going to use the train data augmented here. We were around 84%, right? Accuracy. Let's see how you're going to perform. Okay, 5 epoch. It's going to take more time because it's a big, huge model, pre-trained one, that I'm tune it and adapt it to this problem. And you can see that from the first epoch, let's see how you're going to perform. Amazing, right? 98% accuracy from the first epoch. You see how transfer learning is valuable? It's important. Keep it in mind. When you're working with images, always use pre-trained models and transfer learning. Now, again, transfer learning will depend on the problem that you're working on. Maybe in your field, there is no pre-trained model, and you're going to need to create your own custom one. You see? It depends on the field that you are working on. But in general, when you are working with images, always there are tons of pre-trained models, as this one, MobileNet. You can see 99% accuracy just on 5 epochs. You see how time it saves you, and get the best model already that perform very well on pizza or steak, like this one. Amazing. Now you can save it again and load it again to predict on it, to make some prediction. So I'm going to load it, 99%. Amazing. So now you can create a function to predict these images, for example. like this one. All right, 99% sure that it's a stack, but let's make it more visual using what we call here this function, like this one. You see, he predicted pizza. If I'm going to change it to stack, I don't know if I have, okay. Amazing, stack is predicting very well. Now, in order to make it more visual, there is a library called Gradio, which allows you to create a small dashboard inside your Jupyter notebooks. And it's gonna look like this one. And it's gonna allow you also to share it with your friend using a link that's gonna run only for 72 hours. So it's not that good. So it's just for you to practice and to show if your model is doing very well. Now, how can I test this? I don't know where I put my images. Where can I find maybe training? This one. Let's try to find some. Okay, let's try it on this kind of image. For this example, this one. Amazing, you see? It's a small dashboard that you can use to see how your model is performing. And you can share it with your friends or colleagues. And you can see that you can clear and add another one, like for example, stack here to test it. Okay, amazing, because we get a very high accuracy, don't forget, 99%. This is why you get in this all the time sure, 100% it's a stack. And this is how it looks like, the dashboard that you can share with this link. If you can get this link, you can access to this dashboard, for example, and this model. But it's gonna work only for we have seen 70 hours, which is not great. This is why the last course we're gonna see how you can package all everything locally using, for example, Streamlit. Now, again, final example is multi-class classification. An app food that's gonna able to classify 10 classes. Again, you can always go through these all steps that you have seen and the different custom architecture, but at the end of the day, transfer learning may gonna make it very easy for us. So again, you can always get into these new Jupyter notebooks, play with the different classes, as you can see, different architecture, try to get the best model, but at the end of the day, you can see that it's struggling to predict for 10 classes. It's getting only 0.29 accuracy, because now we are not working on binary classification. We are working with multi-class classification. It's another level. But at the end of the day, I told you, go to transfer learning, same model. And you're gonna see that for 10 classes, he was able to get 85%. Amazing, for 10 classes. This is why it's important to use transfer learning when you are working with images. And finally, you can always use Gradio or create your own dashboard like this one. Let me show you the final thing. Using Streamlit. This is running locally on my machine using the pre-trained model that predicts 10 classes. And now, I can use this dashboard, which looks like a food application for vision that classify 10 classes. You can train new classifier or just use the pre-trained mobile net that you have seen and trained. Now I can test it on 10 classes. For example, hamburger. Let's see how it's gonna perform. Okay, amazing. 99% sure that it's hamburger. You have your 10 classes here. This is the kind of dashboard that you're gonna produce at the end of the deployment of your application at the end, when you're gonna train all and finalize improving all your models. This is the kind of stuff that you can do and create. Again, let's try it on chicken wings, as you can see. Okay, amazing. It's working very good. He differentiating between chicken curry and chicken wings. Okay, makes sense. This is the kind of application that you can do. Now, before I finish, just to give you an idea about the different projects that I've been working on and how we can maybe collaborate and publish papers together, just to show you some of different projects. Let me just run this. Projects. I choose 3 use cases of projects that I've been working on here at Coast. First one is for solar irradiance forecasting project, then genotype to phenotype prediction project, and finally 3D fossil city slice classification. For the first one, the Climate Change Center gave us huge data, 40 years of hourly data of global horizontal irradiance. And they want to do some monitoring and forecasting on that. So for that, we built this workflow, as you can see. Start by getting the data ready, doing some exploratory data analysis, pre-processing it, using different deep learning models, advanced one, LSTM, GRU, for example, convolutional network. It can be done with time series, and transformers. And this is, at the end, we deployed what we call a dashboard with multiple pages, as you can see. The first one was related to doing some EDA. It's a complex data, so they need something to visualize this data, not CDF files. Then another, to make it easy with a lot of different options here, as you can see with the side menu. The second page is for forecasting, to measure the performance of the model, how it's performing, with real data for the region Tabuk here. And finally, to do prediction on new data using these pre-trained models for time series. They're going to choose the date, and they can predict on it. This is the kind of dashboard that you are working on, and you can produce. So the whole pipeline. The second project is genotype to phenotype prediction project. And the object was to develop predictive models on using artificial intelligence for agriculture traits in rice using huge data. They gave us 20K samples of rice with almost 200K features. Their features are called genotypes, chromosomes. And they wanted to predict phenotypes. In other words, they wanted to predict the rice traits, maybe the weight, the length, the ratio. This is the kind of prediction that I want to use. So for that, we developed all this pipeline. And again, we deployed at the end an application like this, where the user is going to use and select the trait that you want to predict, the grain rate, or for example here, grain weight. You're going to put his data, as you can see. And then, after analyzing this data again, you can see that it's going to read the file and give you a preview. Select the phenotype that you want to predict on. Doing, again, I told you, it's almost 200K features. So for that, we need to select only the top and most important features. It's already have been done. This is why I'm able to do it. Then you're going to do some data cleaning on this data, as you can see. And finally, you can predict on these chromosomes and genotypes to predict the grain weight, for example. And they can generate this prediction and download it. Now, these are prototype dashboards. Now I'm going to show you a final product, how it looks like. This is the last example, the 3D fossil city slices classification. that you are working on. And this is how a final product looks like. Let's start the demo. So for that, they gave us, so you can see that it's versatile, right? From climate change, genomics, now geoscience. This is the idea. We are working with all the departments. So here, they gave us 3D models of fossils, 3D fossils. And they wanted to predict from a slice of these 3D models the species. So for that, again, we started by creating the whole data set, so the whole slices for all the models, the species that we want to predict, doing a lot of cleaning on the data, on the images, segmented these images to capture only the fossil, and then building our deep learning classification, like classifier, using advanced one, 7, and we combined 2 to get the ultimate one. And this is of a final product looks like. As you can see, this is running locally. This is application for it. So you're going to have 3 pages, as you can see, the classifier, the 3D slice matcher, because after classifying the species, they wanted to know from which model it comes from. And as you can see, this is the kind of stuff that you can produce. This is the classifier. I'm going to show you just the images, like the pages. You can see that it's an advanced one. It's not like the one before. The one before were like prototype. Now it's a final product using a full stack from backend to frontend. And again, you can see a lot of settings here. You can play with it. Change it to light mode, for example, if you like light mode. But let's run a small example of it. This is a standalone app. It means that you can do everything from it. So let's take a species here, for example. Second one, these are 3D models of the species. And you can extract slice like this one, as you can see, or segmented to get only the fossil. So just to show you a use case, an example of it, proof of concept, let's download this slice. And so let's run our classifier, the pre-trained one. So the user gonna come, gonna look at to this one, for example, he wanna predict from which class it comes from, which species, it's a fossil. You can do manipulation on it, segmented, and classify this image. It's gonna take a while because it's a big one. It was trained on a lot of images, thousands, to predict these species. Here, we have been working on 12 species. Let's see how it's gonna perform. It's gonna take a little bit of time because it's not only loading the model, but doing the prediction also. Now, yes. Now, yes. I'm working on, it's using IBEX. It's using A100, the GPU. All right, perfect. You see, it's get the right species. Ilphilidelia. I don't have any idea about this kind of stuff. I'm an AI scientist. I don't care. I got the right species. This is what I care about. All right, so now I'm going to give you the confidence level. And you can see the different 12 species and the probability for each one. You're going to have some top prediction as this, the winner, and the second one, and the confidence. And you're going to have some confidence metrics like this one. A lot of statistics. Now that I got the real species, I can go to the 3D slice matcher. And let's upload the same image. Now, I know that just to show you the use case, same thing. You can go through the segmentation and everything. And I can select the species, as you can see. The model, I know that it comes from Ephididia. And let's select the one from where it comes, because I know it. This is just the use case, specimen 2. And I can select another model, for example. And let's try to run it and see if you're going to get the right slice from where it comes. There's another problem to resolve. So they wanted something to predict the species, and then from which 3D models it comes. This is the idea behind this. And again, it's running on IBEX using GPU A100. You can see this kind of stuff, how it's very taking time. This is only 2 model. Here, he's gonna try all the different slices, diagonal 1, orthogonal, and he got sure at 0.9 that it comes from the right species and the right model, as you can see. And he got the right slice. He give you the candidate, the axis, and the slice from where it comes. Amazing, right? If you are not happy, you can reduce the threshold and look at to the Minoxia, for example. He found this. Okay, this is why you need always an expert to supervise everything. So this is the kind, he found the right slice, as you can see. Now you're gonna get some statistics, as you can see, and you're gonna get a final 3D visualization of the 3D models and the slice from where it comes. You see, you can play with the details of the model. All in one standalone application. This is a small use case of the project that we are working on. So if you have some data, you want to put some AI on it, don't hesitate to contact us. Me and Didier are gonna be happy to help you and work together on it. And that's it. That's it all for today. Again, this was all packaged. Everything is standalone using Docker, the last course. And that's it. Thank you all. Thank you all. I hope you enjoy it. And I know it's a lot to digest, but you get something from it. Thank you all. Yeah.